Swayam Prabha. Digital India. Educated India.
So last class I have determined the Gmax value of a soil in a example problem. Now I want to determine the G value at a strain level of 0.15%. So let's see that how we can do that. So we know what is the Gmax value. So that is 83393.4 kilonewton per meter square. That is Gmax value. And what are the things I have to measure? One is Gmax, that I have already measured. Another is the tau max. I have to measure tau max also. Then only I will get the strain reference, that reference strain that is required to get the strain H. Okay. So let's discuss how we will get the tau max. What is the expression of tau max? Okay. So to do that, what we are doing, that we are taking a soil element. So this is one soil element. So this is initially at rest condition. So that is your sigma V bar is applied, and vertically and lateral this will be K0 sigma V bar, that we have applied. So this is the stress that is acting on this element. But here now earthquake force is not applied at all. So under this condition, what would be the Mohr circle? Under this condition, what would be the Mohr circle? So what would be the Mohr circle? The Mohr circle will be like this. This is at this condition, where this one is your sigma V bar, which is sigma 1, and sigma 3 will be K0 into sigma V bar. Clear? So this is my first stage, where no shearing is applied, no earthquake force is applied, or shear force is not developed due to earthquake. And this stage, this is my Mohr circle. So this is my your normal stress, and this is shear stress. Okay. Now in the second stage, what the same soil element now is subjected to a shearing. Okay. Subjected to shearing. So now initially there was sigma V bar and K0 sigma V bar. Now we are applying a shearing. Okay, here. So we are applying shearing. Here also we will apply that shearing. That value will be the tau max at the maximum shear that is applied, because I want to determine the tau max. So that is tau max. Now under this condition, how the Mohr circle will change? The Mohr circle will now the Mohr circle will shift, or it will change. Now in the second stage, if I draw the Mohr circle, then I will get, so your sigma V, that is now itself also sigma is V. Initially the tau was 0, so coordinate was sigma V comma 0, and another coordinate was the sigma V, K0 sigma V comma 0. Now there is a sigma V as well as the tau max, and there is another point will be K0 sigma V and the tau max. Okay. So now if I extend this point, because this point on the Mohr circle under second stage will be on this line, because sigma v, your x axis, the coordinate for x axis or the vertical normal stress axis, that is remain same as the first stage, but there will be a tau max is added. So this one point, this coordinate will be k0, sigma v bar and tau max. Okay. Similarly, another point will be the same. Here I can draw. Okay. This coordinate will be sigma v bar and tau max. Now, if I join them, these 2 points, it will pass through the origin. Now, if I draw the Mohr circle, it will, now I can easily draw the Mohr circle. I know the radius and I can draw the Mohr circle, and it will definitely pass through this point. And I can complete the Mohr circle here. Okay. So, initially I drawn the half Mohr circle. Now this is the your second stage Mohr circle. Okay. So now this value is what? This value is the tau max. This value is the tau max, and here that is your maximum stress. So that means here if I draw a failure envelope, then that would touch this point because that is my tau max. Okay, that would touch this point. So suppose this is my failure envelope, this is say phi, and this one is the C. So this value will be C cot phi. Okay, because this is phi, this is also phi. So this value will be C cot phi. Okay, now what is this value? What is this value? From this point to here, this value will be simple this value will be half, that means the center of the Mohr circle, because both the Mohr circle center is same, the center of the, consider the first Mohr circle, the center of the Mohr circle from the origin, that will be equal to half sigma v bar plus k0 sigma v bar. Okay, and for the first Mohr circle, the diameter that will be equal to half sigma v bar minus k0 sigma v bar. Okay, so the your center of the Mohr circle, first Mohr circle that I am talking about, the center of the first Mohr circle will be half sigma v bar plus k0 sigma v bar, and diameter of the Mohr circle, that will be half sigma v bar minus k0 sigma v bar. Now, if this is the point and the failure surface is tangent to that point, so now if I join this point and the center, so this will be 90 degree, definitely. This will be 90 degree. So now if I draw these points and if I write this is O point, say this is my A point and this is B point. Okay. Now from triangle OAB, now from the triangle OAB, what is the OB value? OB value is equal to what? Because you know this is total, this length is how much? This total length is C cot phi plus half sigma v plus k0 sigma v bar, and this is 90 degree. This is your phi. So OB value will be, I can write C cot phi plus half sigma v bar plus k0 sigma v bar, that total into sin phi, isn't it? Because this height, this is 90 degree. So that means I can write that or I should write this is another triangle C. So this triangle should be actually this is not OAB, this should be the triangle OCB. Triangle OCB. So I am taking two triangle. One is OAB, another is OCB. So OCB AB will be, because this is your this, you know, that I can write that sin phi will be equal to OB by OC. Now what is OC? OC value is simple, C cot phi plus half sigma b bar plus k0 sigma b bar. Okay, that is OC. So I can get, if OC is this value, so OB will be OC into sin phi. So OB will be equal to OC into sin phi, and OC is this value. So this will be equal to sin phi only. Clear? Now I will come to the triangle OAB. Now triangle OAB, I have to determine the AB, because AB is equal to tau max actually. AB is equal to tau max. Fine. So from this triangle I can write that my AB square will be equal to OB square minus OA square. OA square I can write from this triangle. Now what is OB? OB is this term. OB is this one. So I can write that OB is half, if I take sigma v outside, 1 plus k0 sigma v bar plus C cot phi, that is equal into sin phi, that is whole square, minus OA. What is OA? So this is actually the OA. OA is equal to this one. OA is equal to this one. So minus half sigma v bar minus k0 sigma v bar to the power square. Then whole term will be half within root if I take AB. So my final expression of this tau max, so tau max will be equal to half 1 plus k0 sigma v bar plus C cot phi sin phi whole square minus half 1 minus k0 sigma v bar whole square, that the total is within root. So this is the expression of tau max. Clear? So this is the expression of tau max. So now I have the expression of tau max. Now let's determine the tau max value. Okay. Now I have the expression of tau max. Now our case, tau max expression, your C is 0. So this part will not exist because C is 0. C cot phi will not exist because C is 0. Because I have developed a general expression. Because our case C is equal to 0. So the expression will be simple. Tau max will be half 1 plus K0 into sigma B bar, okay, into sin phi. Okay. So you can consider, you can erase this bracket. I can erase, sorry. So this is square minus half 1 minus K0 into sigma V bar square to the power half. That is the expression I have written. This is square where C cot phi is 0. So this is square minus square to the power half. So now I put these values. So if I put the values, so this will be half 1 plus 0.384. Sigma V dash is 68. This is 68. You can see this is sigma V is how much? Sigma V bar is 68 kilonewton per meter square. 68. So this is into 68 into sine 38 degree. That is square minus half 1 minus 0.384 into 68. That is, this is square, then total is under root. So that will be equal to 20 kilonewton per meter square. So maximum shear stress will be 20 kilonewton per meter square. So now I will get the strain reference strain, that is tau max by G max, because I have already written the reference strain is tau max by G max. So I know the tau max, which is 20, and G max is 83393.4. So that will be 2.4 into 10 to the power minus 4. Now I will calculate the tau h, which is strain by strain reference 1 plus A e to the power minus B strain by strain reference. Now calculate AB. What would be the AB? So what would be the AB? You can see. So AB, so this is the clean dry sand. No, because this is below the water table. So it will be clean saturated sand. So clean saturated sand, I will use, this is my A, this is my B, and for damping calculation, this will be A1, this will be B1. Why I am using the clean saturated sand? Because sand is under water, okay, below the water table. If it is above the water table, I could consider the dry sand, but now it is below the water table and it is sand, so that's why clean saturated sand. And these parameter I will use, clean saturated sand A, B, A1, B1. Okay, so my A is given is equal to minus 0.2 log base 10 N. So it is equal to minus 0.2 log N is 7, total number of cycle is 7. So that is equal to minus, this is base 10, minus 0.169. Minus 0.169 and B is equal to 0.16. So now if I put this value, what is my strain? Strain is 15 into 10 to the power minus 4, that is 0.15%. So 0.15 into 10 to the power minus 2, so it is 15 into 10 to the power minus 4, that is my strain. divided by reference strain is 2.4 into 10 to the power minus 4. Then 1A is 0.169 e to the power minus 0.16. Then here again 15 by 2.4 I can write 10 to the power 4, 10 to the power minus 4, 10 to the power minus 4 will cancel. So this is the expression, and from here strain is coming out to be 5.86. So my G at strain level 0.15%, that will be G max divided by 1 plus strain H. So that will be 83393.4 divided by 1 plus 5.86. So that will be 12,156.5 kilonewton per meter square or 12.16 meganewton per meter square. So you can see that initially it was 83,393 around kilonewton per meter square. That has been reduced to 12,156.5 kilonewton per meter square. So G value has been decreased. Okay. So at the strain level. So this way I can determine the G value at any strain level. Okay. So I have determined it, but I should know what is the number of cycle corresponding to that strain level. That I have to know. After that I will get the all the at any strain level I can determine the G. Now come to the damping part. Okay. Let's come to the damping part and how I will get the damping. Damping, I know that damping is D by D max, that is equal to strain H 1 plus strain H, but here this strain H will be different because here it is A1 B1, those parameters are different. So here D max I can calculate from this table. Again I go to the D max table. This is D max, clean saturated sand. So D max is 28 minus 1.5 log N. Okay, so that I will use here. D max is 28 minus 1.5 log 10 N. So this is 28 minus 1.5 log 10 7. N is 7. So it is coming out to be 26.73%. Damping is 26.73% maximum damping. Okay. So strain H here will be strain by strain reference 1 plus A1 e to the power minus B1 strain by strain reference. Strain reference will not change, strain will also not change, only the A and B value. This A1 for clean saturated sand is 0.54, that you will get from the table, N to the power minus 1 by 6 minus 0.9. So it is 0.54, N is 7 to the power minus 1 by 6 minus 0.9. So it is minus 0.51. Similarly B1 is 0.65 minus 0.65 N to the power minus 1 by 12. So this is 0.65 minus 0.65 is 7 to the power minus 1 by 12. Okay. So that value is coming out to be 0.097. So I will get the A1 and B1. Now I will put here, this strain is 15 into 10 to the power minus 4 divided by 2.4 into 10 to the power minus 4. 1 A1 is 0.15 e to the power minus 0.097 into say 15 by 2.4. Okay. So it is coming out to be your 4.51. So now the damping will be Dmax into strain H plus 1 by strain H. So Dmax is 26.73 into 4.51 divided by 1 plus 4.51. So this is coming out to be 21.88%. So damping means as strain increases, this D value, damping will reach to Dmax. Okay, so Dmax is 26.73%, the maximum damping. So now at 0.15% strain, damping is 21.88%. Okay, so it is reaching towards the Dmax as strain increases. So now this is the expression. Now I will give you the curve. So now if we can determine that G sec. Okay, so this G I am talking about, this all the G, these are G sec, because this is equivalent linear model. So now if I draw G sec by G max curve versus shear strain, or I should say G by G max versus shear strain, then I will get this type of curve. So this is called modulus degradation curve. Okay, this is called modulus degradation curve. So so that means at low strain level you can see it is low strain level G is equal to G max. So that is your equal to 1, close to 1. And I have given what is low strain level. So generally if you look at this curve, this strain level varies from 10 to the minus 6 to 10 to the minus 1. So in percentage wise it varies from 10 to the power minus 4 percentage to 10 percentage. You can see 10 to the power 1 means it is 10 percentage, and it is actually 10 to the minus 6 to 10 to the minus 1. So that is the general range, but this damping is giving 1%. Why? Because as I mentioned that if it is strain level is very high, then this equivalent approach, if I calculate the damping, so it may overestimate the amount of strain energy. Okay, so there is a possibility of error. So that's why you have to be very careful when you apply these methods for greater than 1%, because the error start before that. But that's why few researchers, they have suggested some correlations and corrections. So I have given one reference. You just read that paper, you will get some more idea. So so this is your G by G max curve, which is called modulus degradation curve or modulus reduction curve, you can say. And this is also G by G max curve, another G by G max curve, and this is your different G by G max curve. This is your damping curve. This is my damping ratio. Okay, this is the damping ratio curve. Also you will get. Now if you look at this curve, then what are these curves are function of which parameters? These are function of, the major parameters are, these are function of sigma m bar or sigma m dash. So sigma m dash is also function of your sigma v dash. Okay, so this is function of basically the effective overburden pressure. Clear? That is one thing. It is function of PI, plasticity index. It is function of OCR, over consolidation ratio, and obviously it is function of strain level. In addition to that, it is function of other factors, that is void ratio, your aging, all those things. But these are the major things. You can see that this is Pi is equal to 0 and this is Pi is equal to 50. What does it mean? Pi 0 means it is sandy soil. Plasticity index is 0. Pi 50 means it is your clay soil. So you can see in that case, in case of sand, the effect of, if your Pi value is less, the effect of sigma V bar, effective overburden pressure, is very significant. You can see the difference is very significant in case of lower Pi value, but in case of high Pi value, this difference is not that significant. So that means if your Pi value is very high, then the effect of effective overburden pressure or the stress effect is not that significant as compared to the case where the Pi value is very low. Clear? So that means in other word I can say, if you increase your Pi value of the soil, the effect of stress or effective overburden pressure on this G by G max curve or modulus degradation curve is not that significant. Clear? That is one thing. And then you can see that as your strain level increases, the G value decreases. So this is the trend, and your damping ratio increases. Okay. So this is your cyclic strain versus damping ratio, cyclic strain versus G by G max curve. So remember one more thing, that's why I want to mention that in some cases you are doing, say, small scale test, say sectable tests, small scale, and you are using this equivalent nonlinear model, and you have developed the G by G max curve for your own soil by doing triaxial test. Okay, but here suppose in your model tank the confining pressure or effective overburden pressure is very low, but it is sometimes or most of the times is not possible to conduct that triaxial test under that low confining pressure. So you are, say, using doing the test under very high confining pressure, and then you have developed the G by G max curve. Now that G by G max curve is using for when you are doing your numerical analysis to simulate that experimental result. You are doing that test, that analysis of using that G by G max curve that you have generated for under a very high confining pressure in triaxial setup, but your actual confining pressure is very low. So that means you have to scale down that G by G max curve also, because you can see it is function of effective confining pressure. For example, you have done your test under the very high confining pressure, 100 kPa, but your in model tank this is hardly confining pressure is very less. So that time you cannot use that 100 kPa curve. And another problem is most of the cases you cannot generate the this G by G max curve by conducting test under that very low confining pressure, which is the actual confining pressure in your model. So in that case you have to use equations. So scale down, so you generate your curve for 100 kPa, then you scale down it for your actual confining pressure which is very low, then that you use for your numerical analysis. Clear? So that is one thing I want to say. Now based on that, Ishibashi and Zhang 1993 they have proposed the expression for G by G max. Okay, so this is another model. So I have discussed about the Hardin and Greenwich model, and then I have discussed how to determine the G value for under any strain condition. But if you use this expression, you can also use get the strain value at any G by G max value at any strain level. And if you know the G value, then you can calculate if I know the G max value, then I can calculate the G value at any strain level. Okay, so this is the expression. You can see it is given, so it is function of Pi, it is function of strain. Here it is given because here it is mostly the major function as this Pi strain, okay, and the sigma effective overburden pressure, sigma B bar. So here it is given, it is in the form of again these three major things, this Pi, strain and sigma m dash or sigma m bar, which is actually the function of effective overburden pressure. So these three major parameters, those I have mentioned here, so those are incorporated here in this equation, and then if you use this equation you can get the G value at any strain level. Okay, so this is the NPI is the function of N is the function of Pi, and M is a function of Pi and strain level, and that means this M function of Pi and strain minus M0, these expression you will get, this whole thing you will get by using these expression. And what is tan H, that is given here. And similarly the K value, this is also function of strain and Pi, that also you will by using these expression. And NPI, N is a function of Pi, so that also you will get from this expression. For different Pi you will get different N value. The Pi is the plasticity index. This is the expression for G by G max. Similarly, this is the expression for damping ratio. Okay, so this is the expression for damping ratio, which first you will get the G by G max, then from that G by G max you put it here, you will get the damping ratio. The same Ishibashi and Jiang propose that equation. So this is the end of your equivalent linear model. Now the one last model that is given, that is the non-linear model. Okay, so non-linear model I will discuss. So that means this non-linear model, it is describe the response of the soil under cyclic loading, but it follows these 4 rules. Okay, I will discuss one by one these 4 rules. So that means these non-linear models, again this is expressed in terms of this backbone curve. Now because here I will discuss only the simple non-linear model. So and then you can use the advanced constitutive model also when you do the non-linear analysis. So but I will discuss a simple non-linear model and then how it follows that. So let me discuss that thing, that again this is your shear stress by shear strain. Sorry. This is shear strain and this is shear stress. So this is your backbone curve. Again this is your tau max, the same thing that we have discussed in the equivalent linear model, and this initial one will give you the G max. Okay, so again here also this tau is represented by G max into strain 1 plus G max by tau max into strain level. Okay, so tau max, you know, that is the high strain shear strength. And G max is equal to initial low strain stiffness or modulus. So now this expression is been expressed by this FBB, which is a function of F, G max strain 1 plus G max by tau max into strain, where FBB is called backbone function. So that means it is represented in terms of backbone function, this expression is represented. So in the non-linear model, the characterized by the backbone curve, this backbone curve, and it has to follow a series of rules. So these are the rules. So let me explain that. That first rule, that means you have to follow these 4 rules. The first rule, during initial loading, stress strain curve follows the backbone curve. Okay? If the stress reversal occurs at a point, the unloading and reloading curve follow the same shape as the backbone curve, but it enlarged by a factor of 2. If the unloading or reloading curve exceed the maximum path strain and intersect the backbone curve, it follows the backbone curve up to the next stress level, stress reversal. If an unloading or reloading curve crosses an unloading or reloading curve from previous circle, then it follows the stress strain curves of the previous circle. If the any models follow these 4 rules are called extended meshing model. So let me explain by these 4 rule by one example or just one loading. So this is your tau shear stress versus time. This is shear stress versus time, and here I can say this is my stress strain curve that will follow this nonlinear model. This is the shear strain and shear stress. So first I will draw the backbone curve, say. So this is, say, backbone curve. So it is characterized by the backbone curve. This is, say, backbone curve of that soil. So first one is, if I start that first your loading start from A point. So it will go and then it will reach the B point. So what the first rule is saying, that the during initial loading, stress strain curve follow the backbone curve. So it will follow that backbone curve. So it will follow the backbone curve. So it start from A, then it will go to B, it follow the backbone curve. Now it's saying that if a stress reversal occurs at a point, the unloading and reloading curve follow the same shape of the backbone curve, but is enlarged by a factor of 2. Now what will happen, say now there is a stress reversal. This is stress reversal, it is going down in the opposite direction and it will go up to the C point. There is stress reversal. Now here also there will be stress reversal. So it will be stress reversal. So it will unloading and reloading curve follow the same shape of backbone curve. So it will come and then it will follow the same shape, but it is same shape, so that it will be continue here, and if the unloading and reloading curve exceed the maximum path strain and intersect the backbone curve, it follow the backbone curve. Now it will go here, okay, and it will intersect that backbone curve, say. So this will be C point, say. It will intersect backbone curve. Now what will happen? It will, now this loading is extended up to D. Okay, it will extend it up to D, say. So now it will also follow the backbone curve and it will also go up to the D point. It will up to the D point, it will also go up to the D point, because the third rule say that if it intersect backbone curve, it intersect backbone curve at C point. So now it will follow the backbone curve until or up to the next stress reversal. So it will continue up to D, but because why D? Because in the D point there is another stress reversal. So it will follow up to say E. From here it will go up to E. So it will also, from here again it will go, and then again it will intersect the E point. So when it is intersect the E point, then it will again follow the backbone curve unless or until there is another stress reversal. So it will be here, say F. So it will also follow the backbone curve up to F, because there is now the next stress reversal, it is going down and it is up to say G, up to G. Now I will go back to G, this is say G, but here G it has not intersected the backbone curve, so it will not follow the backbone curve, because before that there is a stress reversal up to say H. So it will follow then again this path H up to H, and then another stress reversal, say, so it will follow like this. So this way it will follow the stress strain path. So then if any model is following this thing, these 4 rules, then it is called extended meshing model. And if you see that if the unloading or reloading curve crosses an unloading or reloading curve of previous cycle, it follows the stress strain curve of the previous cycle. Clear? So that is also another rule. So this way we can generate the stress strain curve for this nonlinear model. So remember that this is a very simplest model for that is been extended, explained for the nonlinear model. So there are some advanced constitutive models are there, but the thing is that these parameter estimation for these advanced constitutive models are the parameter estimation we have to do, that is tedious. Okay, so in that sense, still equivalent linear model is popular and it has been applied in geotechnical engineering problems along with that nonlinear models or advanced constitutive models. So this is the end of this determination of or measurement of dynamic soil properties and the stress strain behavior of cyclically loaded soil. So this is also the end of module 3. So next class I will start the module 4, that is 1D ground response analysis. Thank you.